We had been talking about the energy approach applied to systems. Just a summary, as with momentum, the forces that are acting with a system, you split up into two categories, external and internal. And it's external forces that actually can add or subtract energy through the work that they do. So the work done by external forces can add or subtract energy. It can transfer energy in or transfer energy out of the system. Internal forces don't do that. They keep this amount of energy the same in the system. But they're not unimportant. They can change the form of the energy inside the system. And we talked about two kinds of internal forces, conservative and non-conservative. Conservative forces will, if they're internal forces, can change kinetic to potential or potential to kinetic. They can do that. Now, non-conservative internal forces will turn kinetic or potential energy into internal energy. In other words, typically they'll make the object heat up. So we have talked so far about two conservative forces, gravity and friction. Not friction, spring force. And the non-conservative force that we've talked about was friction. Okay, and so one very special case of all this is the big picture right here, but one special case is if you have no external forces, which is what we call an isolated system, and you do have internal forces but they are all conservative, okay, then, so you're not adding any additional energy or taking away any energy, so the total energy stays the same, and if you don't have any non-conservative internal forces, none of that energy is being transformed into internal energy, raising the temperature, for example. So it all stays mechanical, in other words, kinetic plus potential. Mechanical energy means kinetic plus potential. So your total kinetic plus potential energy stays constant. It still can, the individual K and U can change, but their sum has to stay the same. And so this is called conservation of mechanical energy for a system. And this is a very powerful tool to apply in a lot of problems. Before we start attacking some problems, let me address one more thing. How do we know if a force is conservative? We talked a little bit about this in class. Gravity and gravity and spring force had the ability to store energy that we could get back in the form of kinetic energy. So that's what we call potential energy. But there's also a test, sort of an easy to apply test for whether a force is conservative or not. And you look at how the force does work. And if the work that it does only depends on the starting and ending points, and not how you get there, not on the path you take from that starting point to that ending point, if the path doesn't matter, then it is conservative. So we saw this in gravity because if an object starts at a height and then drops straight down, we figured out the work that was done. Or if it was on an incline and it started at a height and went down diagonally, it didn't matter. It was the same amount of work because our expression for work was just, for gravity, was minus mg delta y. So all that mattered was the change in the y, right, which is just your final y minus your initial y. And it didn't matter how you went in between. And in fact, if you started here and did all kinds of crazy maneuvers but ended up in the same place, gravity would still do the same amount of work. And so it only depended on the starting and ending points, not on the particular path it takes. So that's why it was conservative. And it's the same with a spring. If a spring starts at one position and then later on ends at another position, we figured out that the work done by a spring was 1/2 k x I squared minus 1/2 k x f squared, and that formula only asks for the beginning and the end x's. It doesn't matter what path it takes. It doesn't matter if we just pull it straight back, or if we pull it back a little, push it in, pull it way out to here, and then pull it and then bring it to xf finally. The overall net work done by the spring force will still be the same. So the path doesn't matter. Whereas finally for friction, work done by friction, certainly it would matter if we take an object and let's say we're looking down on a table and the object is here, and if we move it over to here, then let's say a distance d, the work done by friction will just be the frictional force, so it'll be kinetic friction because we're moving, times d, right? Because work is force times distance. But if we instead moved it over here and then down here, well, it will have traveled farther. So the new, I'll call it d prime, like the new distance that it traveled, that'll change, and so the work done will change. And so the beginning and ending points were the same, but the path matters. If we took the shortest path, we'll have the least amount of work done, but if we take a longer path, more work will be done by friction. So the path matters, and that's why it was non-conservative. Now, why this test applies and what that has to do with the ability to store energy is a little bit, there's some math behind that that I'm not going to show you, but I wanted to at least expose you to this test. It's a way to tell if we encounter a new force and we want to know if it's conservative or not, we can think about work done and try to decide how this test will come out for that force. Okay, on to problems. So we had started a roller coaster problem in class, and I just want to complete it. So this would be an example of conservation of mechanical energy. Because we have a roller coaster that starts up here at rest. I gave you the mass of 1,000 kilograms. And it's going to go along the roller coaster. And it's isolated. There are no external forces acting. Actually, there's the normal force, right? The normal force of the track pushing up on the coaster. Ignore that for just a second while we complete the problem. I'll address that afterward. Normal force is a little bit special. It's going to turn out that normal force can be an external force, and you can still apply conservation of, you can still kind of call it an isolated system for the purposes of mechanical energy. Again, I'll talk about that later. But okay, so except for normal force, there's no other force on the coaster Earth system. That's our system. Gravity is, of course, a force acting on the coaster, but if we make it the coaster and the Earth together as the system, then gravity is now internal. And gravity is a conservative force. So it's isolated, and the only internal forces are conservative ones, just gravity. And then that allows us to say, okay, that means total mechanical energy, kinetic plus potential, will stay constant. It's just that the K and the U individually can change, but they'll always add up to the same thing. And so we looked at point A, which is at the very beginning, and we said, okay, it's at rest, so it has no kinetic energy, but it does have potential energy because it's 25 meters up in the air. And our formula for potential energy, which we figured out in the last class, was mgy. And you work that out, and it was 245,000 joules. So the total mechanical energy is 245,000 joules. Now, again, because of conservation of mechanical energy, that can't change. The roller coaster Earth system has to have 245,000 joules of mechanical energy for this whole trip. It's just that it won't be split up in this way. It won't be zero kinetic and all potential. So we use that. So we go down to B, and at B we're down at the ground, so we know we have no potential energy because Y is 0. And so we must have 245,000 joules. All that mechanical energy must now all be in the kinetic energy column, right? So it's all in the kinetic, and then you can figure out what the speed is based on that, right? Because velocity is square root of 2 times the kinetic energy over the mass, and we did that, and we got 22.1 meters per second. Okay, so that's what we had figured out so far. Let's keep going now. Let's imagine the coaster going upside down through this loop-de-loop, and right at the top we're calling that point C. All right, so at this point, we're 12 meters up above the ground. So we'll have 1,000 kilograms times 9.8 meters per second squared times 12 meters. And that equals 117,600 joules. But again, we know we have to have 245,000 joules in total, so kinetic must account for the rest. So it'll have some kinetic energy. So 245,000 minus 117,600 is 127,400 joules. So again, what I'm doing there is I'm doing the 245,000 minus the 117,600. That's how I'm getting that, because I know it has to add up to 245,000. And I'm sorry, I called these should all be C's, right? KC and UC. All right, and then I can figure out how fast it's going. Now that I have the K, and when I put that in, I get 16.0 meters per second. So that's how fast it's going up at the top here. It has to be. Okay, and then finally D, same thing. It's just more of the same. So at point D, we're 8 meters above the ground. So instead of a 12, we put in an 8, and we find the potential energy is 78,400 joules, which means the kinetic energy at that point must be 245,000 joules minus that, or 166,600 joules, which we can translate into a velocity, into a speed, and we get 18.3 meters per second. It's going faster there because it's lower down, so more of the energy can be used for speed, can be used for kinetic energy. All right, and finally, I can also turn the question around and I can ask, where would the roller coaster have to be? Let me write this down. Where is the roller coaster? Where would it have to be when it's going 6 meters per second? Okay, so in this question, we would know K. So we put in 6 meters per second in for V, 1,000 in for the mass, and we get a kinetic energy of 18 kilojoules. And so therefore we can deduce that the potential, again, we have to total 245,000. So that would be 227,000 joules. And then from there we can figure out the Y. So Y will be U over mg. So 227,000 joules over 1,000 kilograms times 9.8 meters per second squared, giving 23.2 meters. So the roller coaster would have to be 23.2 meters above the ground to be going 6 meters per second. So that would be somewhere up here. So actually, the way I drew the roller coaster, there's only one place. It would have to be like right around there at 23.2. Okay, so this is a very typical application of conservation of mechanical energy. I'll stop this particular video here and pick up in a second part.